Oke. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen.
That's okay, you can speak Indonesian.
Okay.
You can speak Indonesian.
Okay, you
Try
can.
to understand it.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi. Salam sejahtera untuk kita semuanya. Bapak Ibu yang saya hormati, yang sangat kita banggakan, Dr. Wilford Lie from the School of Molecular and Bioscience, University of Wollongong, Australia. Our distinguished lecturers and our beloved students. Pada kesempatan saat ini, izinkan saya memberikan salam hangat kepada semuanya, terutama untuk event hari ini, yaitu tentang guest lecture yang akan diisi oleh Dr. Wilford Lie. Terima kasih untuk bisa hadir bersama-sama pada hari ini. Semoga hari ini kita bisa belajar banyak dari Dr. Lie yang akan memberikan guest lecture pada pagi hari ini. Sebelum saya memulai, izinkan saya juga menyampaikan apresiasi kepada Mr. Han dan Miss Yusi yang sudah menyelenggarakan kegiatan ini dengan sangat baik. Semoga apa yang Bapak Ibu berdua lakukan menjadi amal ibadah untuk Bapak Ibu. Pada hari ini, Dr. Wilford Lie akan memberikan pengalaman dan ilmunya kepada kita semuanya tentang NMR spektroskopi. Khususnya mulai dari basic sampai ke aplikasi dari NMR. Terutama untuk molecular structure elucidation yang memang sedang diambil mata kuliahnya oleh anak-anak untuk semester ini. Jadi semoga dengan kehadiran Dr. Lie pada guest lecture kali ini memberikan manfaat untuk kita semuanya. Ya, jadi Ibu berharap Anda semuanya jadi lebih paham tentang NMR. Walaupun kita tidak memiliki alat spektroskopi tersebut, Anda bisa belajar dari guest lecture atau video atau yang terkait dengan NMR, tapi karena ada ahlinya hari ini, maka silahkan. Kesempatan ini digunakan sebaik mungkin untuk bisa bertanya, berdiskusi, mencari kesempatan-kesempatan untuk bisa memahami lebih jauh tentang NMR. Ya, nah sekian dari saya. Saya berharap semoga kesempatan ini dapat digunakan sebaik mungkin. Ya, kemudian untuk Dr. Lie, kami berharap tidak hanya bertemu secara online, tapi suatu saat nanti Dr. Lie bisa mengunjungi kami di Universitas Negeri Jakarta. Terima kasih sekali lagi. Saya kembalikan ke Pak Han. Semoga acara ini berlangsung dengan lancar dan sukses dan bermanfaat untuk student kita semuanya dan menambah pengetahuan juga untuk Bapak Ibu dosen. Demikian dari saya. Mohon maaf karena dalam perjalanan ke Universitas Indonesia dalam rangka kolaborasi pemanfaatan laboratorium untuk penelitian. Demikian, terima kasih sekali lagi. Wassalamualaikum warahmatullahi wabarakatuh. Saya kembalikan ke Pak Han.
Thank you.
Yeah, thank you, Professor Muktiningsih, for the welcoming speech. And now we will give the opportunity to our guest lecturer today, Dr. Wilford Lie, to deliver his presentation. But before the presentation start, I will introduce him to all audience in this session. Dr. Wilford completed his doctoral degree at Massey University in New Zealand, where he learned quantum mechanics and NMR spectroscopy from Paul Colligan, Craig Eccles, Herbert Wong, and Paul Atkinson. I'm sorry if I was mistaken
No, that's okay.
the name. He then worked as a postdoctoral at the University of Canterbury for 2 years before moving to Australia to work for the University of Wollongong as an NMR facility manager and lecturer till now. His research interests focus on theoretical NMR, experimental NMR, NMR data processing, and NMR spectral analysis. He is an author in 29 publications with around 650 citations in a wide range of research, ranging from biomolecules, organic molecules, and natural products in drug discovery to nanotubes, advanced electrode materials, and electrolytes for high energy density batteries. Very broad of research topic, I think. He loves teaching and keen on passing his knowledge and is a well-respected scholar and lecturer by many students, academics, and researchers domestically and internationally. So without any further ado, please welcome Dr. Wilford Lie. The
Okay,
stage
thank
is
you.
yours.
Very good, very good, very good. Could I share my screen?
Yes, please.
I'm going to share my entire screen so that it will be a bit faster.
Yeah.
What do you see on the screen?
It's
See my
the
entire
computer
screen, is it
desktop.
correct or
Yeah.
not?
The computer desktop screen.
Okay. What do you see on the screen?
Now, PowerPoint slides.
Table of contents. Is that what you see?
Yes, table of contents.
Okay, okay, that's good, that's good, that's good. Very good, very good. On my side, I can't listen to yourself properly. It's a bit weak for some reason. I hope you can hear myself clearly. Can you hear myself clearly?
Yeah, it's very clear. Yeah,
Very
it's very clear here. Yeah.
That's the main point. Okay, welcome everyone, and thank you for participate in this lecture. Today, what I'm going to do is to go through quickly one of the lecture series that I usually talk about in one of the subjects. And then in the end, we're going to go through the problem solving. The first stage will be a bit faster because there's plenty of things to talk, but I'm not going to talk in details of the difficult part of it. For example, the mathematical part of it. We're going to focus on biomolecular NMR and problem solving. You are welcome to interrupt me if you have any question to ask. I'm quite happy to have any kind of interaction between you and me. Okay, let us start. Can you see this on the screen? It's a full screen. Could anyone say that you can see this full screen?
Yes. Yes, we can, sir.
Very good, very good. This is one of the courses that we taught in this university.
Yeah, it's perfect, actually. Yeah.
This is for advanced NMR spectroscopy. So usually we go to fundamentally, and then we get the laser. Okay, or laser pointer. Okay. So we go to fundamental NMR equation. Go to and talk about the local field, chemical shape, nuclear spin, etc., etc. And then at the second stage, okay. Now we talk about biomolecular NMR, and today I'll focus mainly on biomolecular NMR. But before I do that, I'll quickly go through the content that I usually talk about in this subject. It will be a very quick, because a lot of them are a bit difficult to consume and need a lot of time to explain. Here is something about the fundamental equation of NMR. I think everyone should be familiar with this. This is a fundamental equation of NMR. In brief, we talk about the frequency being directly proportional to the gyromagnetic ratio and the strength of magnetic field, of the external magnetic field. I think that is probably very easy for you to understand, because everyone talk about that. This is about the high gyromagnetic ratios, between gyromagnetic ratios. And it's also an easy part. Talk about local magnetic field, which is a contribution, of the local magnetic field to the chemical shape. And we talk about chemical shape, and this is the definition of chemical shape. We talk about a general idea of the nomenclature of chemical shape. This is a shielded region, this is a shielded region, upfield, downfield, etc. We usually do a summary. We talk about spin quantum number, which you are also familiar with. For example, proton spin half particles, and deuterium spin 1 particles, etc., etc. We also talk about the energy. Spin half particle, for example, has an energy graph like that. When the magnetic field is 0, we have no splitting in the energy. With the magnetic field being bigger and bigger, the splitting of energy level between the two different energies are getting larger and larger in this case. We talked about an important concept that we get from quantum mechanics, which is delta E equals the resonant frequency. This is based on the energy unit in H zone, where H is a Planck constant. So in this case, the energy level difference is simply equal to the resonant frequency of the sampling of the nucleus. Okay, we talk about Boltzmann distribution. With this, in the end, we concluded that N1 with the N2. In other words, the population of lower energy level is slightly higher than the population of higher energy level. So we also talk about the correlation between the net population and the other 4 parameters here. One of them is total population, and is gamma, gyromagnetic ratio, and B naught magnetic field, and inversely proportional to the temperature. So this is about the Boltzmann distribution law. We talk about the macroscopic nuclear magnetic moment and not being related to a number of parameters in this way. And we simplify this equation to be m naught proportional, being proportional to the n total, multiplied by these two vectors and divided by these two factors. This comes from the last slide. The last slide, we got a conclusion of this, With this substituted into this equation, you'll get this related. We talk about NMR receptivity. In the end, we conclude that the NMR receptivity is directly proportional to the gamma, the cube of gamma cube, where gamma is gyromagnetic ratio. Now, the important thing is the relative receptivity, which is usually relative to the receptivity of carbon-30. In this case, we've got a formula in like that. This list of tables gives you the fundamental properties of nuclei, where we have nuclear magnetic moments for different kind of nuclear species. And they have different spin. For example, proton is spin half particle, deuterium is spin one particle, etc., etc. So in terms of gyromagnetic ratio, on this list, proton have a gyromagnetic ratio of 42 point something megahertz per Tesla. And the NMR frequency for different kind of spectrometer, this is 400 megahertz, 500 megahertz, 600 megahertz. They have different frequencies for different things. For example, carbon, for 400 megahertz is 100 megahertz. 500 megahertz is 125 megahertz. For 600 megahertz, it's 150 megahertz, etc. And we have a small summary of the previous slide. We'll talk about what the magnetic resonance is. This definition of the resonance in physics. When we talk about historically how NMR is collected, it's fixed with the magnetic field and varied with the receiver field, receiver coil. And this is how NMR, the first NMR signal was collected, which is in 1938. At that time, they can only collect one NMR signal at a time. But since 1970, people invented what's called pulse field NMR. It's actually pulsing the whole sample with the RF pulses, within RF pulses. And in the end, do a Fourier transform to get this, to get an NMR spectrum. So this is an advanced NMR starting from 1970. I'm going to explain how the RF field excites the nuclei. We say that the RF field, oscillating field, which is an RF field. RF means radio frequency field. And that can be decomposed into two magnetic fields, B1 and B0, where B1 is defined like this, B0 is, B2 is defined like this. If you add this together, like what this is here, you see that the B oscillation in the end, if you add this together, it becomes something like that because this cancels with this. Now we can see that this is actually a rotating field. This is a magnetic field, it's a rotating field. It's not physically rotating, but it is divided into two rotating fields that are adding together to form an oscillating field. But this component, B1, is the one that is affected to excite the nuclei. So that when the D1, the frequency of D1 is W naught T, is a resonant frequency, meaning it's a resonant frequency of the nuclei, when the nuclei got excited. This is the same concept that we can see in this fundamental equation of nuclei. This simply tells us that whenever there is a magnetic field, whenever there is nuclei will spin with frequency like this. So if you go to the thing that we just showed you, now B1 is the rotating field, and the magnet, the nucleus is rotating at the same frequency. Therefore, B1 is static to the nucleus, or nuclei that rotate with this frequency. Because B1 now becomes static to the nuclei, Therefore, the fundamental equation works. Therefore, the nuclei got excited. So there's a frequency, there's a basic idea of the RF field. We talk about laboratory frame and rotating frame. The rotating frame is a frame that rotating at a frequency that is the same as the nuclear resonant frequency. It's just the same as the merry-go-round. If you are on the merry-go-round, you see something, you can see something, you can see your neighbor or person on the nuclei very clearly. If you're outside the merry-go-round, you can see clearly. This concept of the rotating frame would simplify the equation. So in the rotating frame, the laboratory frame, if you apply a 90-degree power, the nuclear magnetic moment was excited this way, and it came to the end to lay onto the minus y axis of the rotating frame, of the laboratory frame. If we use a rotating frame to observe the excitation, we simply observe something that is flipped from here, from this orientation to this orientation. We didn't, on the rotating frame, we didn't see a phenomenon like that. So this idea of introducing the rotating frame, in fact, we can simplify the presentation to be something like that. So if you apply a 90-degree field, if M is initially here, it will be flipped from this orientation to this orientation. If you apply a 180-degree field, it will flip from this orientation, which is here, to this orientation. So this is the idea of pulsing, The reason why we have to do the pulsing is primarily for observation. When the M naught is orientated this way, which is an equilibrium status, parallel to the B naught, there's no observation we can do. We can only observe NMR signal when it's after it is tipped to that, and let it relax and it will spin. And then we can then relax, we can then observe the NMR signal with a coil that is surrounding the sample. This is just the explanation of that. If you drive a car, you know that there is an alternator this is alternator in the car engine. This alternator is actually, there is actually a magnet in the middle of it. In the middle of it, there's a magnet. This is, you see the coil here? It's a magnet. When we spin this, it spin, and because the magnet is spinning, we can create the current from this alternator to provide the current that we need to start the motor. That's how it is. NMR is the same thing. You see that? This is the M naught on the XY plane. When it's relaxing back, it rotates this way. When you put a coil somewhere here to collect the signal, then because the rotating magnet create some current in the coil. That's the NMR signal that we collected. Okay, this is the basic principle of NMR signal collection. We talk about T1, T2, and T1 relaxation and T2 relaxation. T1 is relaxation. It's for the Z naught, for the MZ to relax from the XY plane to the Z axis. Therefore, initially, if you look at the previous slide, initially MZ is not, because this is on the XY plane. When you rotate, you get back. So M naught in the end, at the equilibrium, it becomes something like that. So to start with, it's not, MZ is not. And then it's gradually increased to the maximum value with time. This is in time, 20 seconds later for this equation. So this is the concept of T1 relaxation. T2 relaxation is another concept. T2 relaxation is something we collect on the XY plane. So it is the starting value is very big. It's the largest value when it first started. With time, it gets smaller and smaller. If you look at the back, If you look back from here, this T1 relaxation, this T2 relaxation, right? Now, at the T naught, we start correct the relaxation data. At the T naught, M naught is the largest. Therefore, the magnetic field is stronger. With time, it relaxes back, and then M naught becomes smaller and smaller. M naught becomes MX and MY become smaller and smaller on this XY plane. Therefore, the signal becomes smaller and smaller. In the end, M naught becomes 0, and MS and Y, of course, becomes 0 as well. So this idea why we have this kind of signal that we collected. It's what we call this is decay signal. The signal is called free induction decay. It's a decay signal. It's a decay signal due to a free rotation of the nuclei. So that's why it's an induction, free induction decay. It's an induction because the signal has come from this magnetic moment being rotating that induce the NMR signal to the coil surrounding it. That's why it's called free induction decay. So that's why free induction decay is always like that. It comes stronger first, gradually decrease. In the end, it becomes 0. So this is about T2 relaxation. So this is the NMR signal we got. This NMR signal we got. It's always something like that. So if we do a Fourier transform of the previous signal that we got, the free induction signal that we got a real signal looking like that, which we call Lorentzian shape. You see that it's very sharp here, and it can gradually reduce to something very broad at the bottom. So this is the Fourier transform of the free induction decay. It usually looks like that. Now we talk about T1 and T2 relaxation, where this is T1 relaxation. This is a T1 signal. This is a T2 signal. It's how T2 signal change with different frequency. Well, for the higher frequency, the T1 drop with time. The T1 drop with time. The T1 and T2. And T2 also drop with time, but for the high frequency, for the high frequency, will keep dropping. For the low frequency, it will be going this way. This one here is a T1. It's a T1 signal. This one here is a T2 signal. Sorry, the T1 time. This one is a T1 time. This one is T2 time. So the T2 time become longer in this case, compared with this lower frequency, this higher frequency, this is for the large molecule, this is for the small molecule. For the small molecule, they're about the same. T1 and T2 are about the same. For the large molecule, T1, T2 are significantly different. So this is about T1, T2. So we talk about dipolar perturbation. This particularly strong in solid state NMR. And then to eliminate this, people found that if dipolar magnetic field actually proportional to this factor, this expression here, in which we have 3 cosine squares theta minus 1 as one of the factors that define the magnetic field strength of the dipolar. What's the dipolar? What's the dipolar field? Suppose this is a nuclear. It's a nuclear. This is another nuclear. That's another nuclear. So this nucleus, because both of them are dipole, therefore it appears to be a dipole. Appear to be a dipole, a magnet to this nucleus. Therefore, because this appears to be a magnet, this will affect the frequency of this one, because of the fundamental equation. Whenever you have a magnet, you have a magnetic resonance frequency. So to eliminate this, we just simply make this equal to 0. When we make this equal to 0, then we don't have the dipolar field. We don't have dipolar field. We try to explain it with this figure here, but that is a bit complicated to explain. We can't have time to explain it. We talk about the block equation, which is also very complicated. And it's differential equation. It's ordinary differential equation. We explain it using this part of the slide. And then in the end, we say that the mx and my here can be combined into a magnet called mxy, defined by mx plus I my, which is a complex magnetic field. So that things become more and more complicated. When we talk about the block situation, and then we talk about the solution of this. We talk about the solution. In the end, we got a solution like that. mxy is a solution of this. If you have looked at this one here, the solution, you got three factors. One of them is just constant. It's not constant. These two factors are important factors. One of them is such a rotating factor. We call it spinning factor. The other one is a decay factor. Then m naught, which is equal to mz in this. M naught minus mz. Obey this equation for the solution. So usually we're only concerned about mxy because this is what NMR signal is. So we talk about the solution of simplification. We talk about this equation here, where this factor here, we call it spinning factor, and we call this waning factor. Waning means gradually decreasing, gradually disappearing. It's a waning factor. This is decaying factor, decaying exponent, which we're somewhere here, and somewhere here. So NMR signal actually is a multiplication of a spinning factor and a waning factor in which the decaying exponent is something like that. It's 1 over T2. It's 1 over T2. We talk about Fourier transform. We try to understand why Fourier transform can actually give us NMR spectra from a induction decay. Then in the end, we figure out that Fourier transform is actually a convolution of two Fourier transforms. The Fourier transform of an NMR signal, which is ST and WT, as we indicated before. ST is a spinning vector, and WT is the waning factor, which is here. If we forget about the M naught here. So the Fourier transform of our signal, is simply the evolution of the Fourier transform of the spinning factor and the Fourier transform of the waning factor. And the solution is very simple. It's the Fourier transform of the waning factor that's centered at the J. Where does the J come from? The J comes from here, because here we got J before, remember? Here we got the J. That's where the J comes. So after Fourier transform, we actually have a very simple form of this. So the Fourier transform of NMR signal is a Fourier transform of the waning factor centered at the resonant frequency. So if you look at it, from the graph, see that this is after the Fourier transform. It is a peak, centered at omega J. This is where it's centered. This peak here is a Fourier transform waning factor. Fourier transform waning factor. It becomes something like that, centered at omega J. And in fact, this is what we see in our NMR spectrum. That's another thing that we usually don't see, which is the dispersed thing. It's an imaginary part. We usually don't display imaginary part in NMR spectrum. That's why you don't see it. But with good software, you can display NMR, can display this. But that doesn't really matter. What we understand that this is actually a 90-degree shift of this one. So if you do a 90-degree shift of this one, you actually get something like that. We can show you in the end if you really want to some NMR processing software. Now, in this slide here, we talk about the quantum mechanics formalism of NMR. We start with the swing digger, which is very famous. It's a fundamental equation in quantum mechanics. It is a bit complicated to talk. I need a lot of time to explain. But in the end, the solution of this equation is very complex. This is a metric. This is a vector. This is a vector. This is a imaginary part. Imaginary part of this part here. This is called in the end you got something called super operator. This is a super operator. In the end, the solution of this becomes very simple, very simple. This H here is a metric multiplied by another vector, which is a column vector, equal to the energy level. This is a vector, then the level is the vector. Multiplied by, or product, multiplied by the state vector. Icon vector. What we call this icon vector. So in the end, this equation, the solution becomes very simple. If this is a bit not very intuitive, if you look at the example, it becomes simple. Say the H here, where the H is in the Schrodinger equation somewhere here, it's a metric. It's a metric. It's a metric divide that can be derived by the energy level, total energy level. If you add the total energy level together, in the end, you get something like that. So we know that this now is a metric that looks like that. And where the omega naught is something like that, and the delta is something like that. This becomes frequency. Can you see that? This is the frequency of two spin half particles, two protons, for example. Proton 1, proton 2, for example. Is the frequency of them. This is the average of these two. This is only for two spin half. So two spin half system. This for simplification, simplify the discussion. So this is simply the difference between the frequency of these two. For example, you've got two protons in the spectrum, different frequencies, different wavelengths, 2 peaks, for example. That is the average of these 2 peaks. This is the difference of these 2 peaks. Okay. Now it's even simple. In the end, you can derive that. You can derive from this, from given you this, which is A, and given you this eigenvector. In the end, the solution will give you 4 energy. E1, E2, E3, E4. That means that you have 4 lines or 4 peaks, or in our term, 2 doublets. Because each of the components represent an energy level. So you got 2 doublets, 4 components. Therefore, there are 4 energy levels. So if you name this E1, E2, E3, E4, which is something like what you see on the screen. Okay. Where you got R and J is defined by something like R is defined by J squared J squared plus delta squared, J is coupling constant, delta J, and take the square root of this. This is where the I is. If you look at this, it's actually Pythagorean theorem. Very simple, very easy to remember. So the beauty of this is that we got E. We got E here. Okay. Now, once we got E, we got frequency. Now remember, in the previous slide, we talked about delta E equals to resonance frequency. If you look at our previous slide, somewhere here. Next slide. Okay. You see that delta E equal to frequency. Time H bar here. H bar is some Planck constant. It's called a reduced Planck constant because it's divided by 2 parts. This is called Planck constant. This is called reduced Planck constant. So you see that delta E equals omega naught. If we make the H bar, the unit H bar, make the unit H bar being the energy unit of this expression, then we can get rid of the H bar. Right. So just remember this equation and this equation here, and then we come back to something here, come back to our previous discussion about quantum mechanics. Right, go to page 12. See, we got the energy already. What we need to figure out where these two peaks are, these two doublets are. It's only to work out the difference between the energy. And the next slide tells us how to make up the difference. So if we want to, we've got two differences: 2, 1, 3, 1, 4, 2, 4, 3. In fact, you can work out. There are actually 12 of them. 2, 1, 1, 2. 2, 1, 1, 2 is the same. 2, 1, 1, 2 is the same. 4, 3, 3, 4 is the same. 3, 1, 4, 1, 3 is the same. 4, 2, 3, 4 is the same. We've got something else as well. But in the observation, we only focus on these 4 frequencies. So remember, we got delta E equals omega. Now, what about delta E Ji? Ji is different subscript. And we got a set of 4 energy levels. And that gives us the frequency of 2 doublets. Okay. So quantum mechanics is very complicated, very hard to understand. But if you know how everything comes from, in the end, you understand it. At least it helps us work out the frequency, which is what we see in the next slide. You see that we've got 2 doublets here, 2 doublets here. This 2 doublet collects into two singlets. If the J coupling constant is 0, it's very interesting and very easy to understand. If J equals 0, these 2 collect into 1. Same case here. If there's no difference in resonance frequency, this is different in the frequency delta. What about if there's no difference in resonance frequency of them? Then these 2 collect into 1. So these 2 doublets appear in different conditions. It depends on that. Okay. J and R, J over R. If J over R is significant, then we got 1 minus something, 1 plus something. This is 1, minus something. You can see something. Okay? Sorry. 2, 1, 2. Let's try 2, 1, 2, 1 here. 1 minus something. So some minus something somewhere here. 1 plus something somewhere here. Somewhere here. So -1, minus something gets smaller, plus something gets bigger. The same case here, minus something will get smaller, plus something gets smaller. So this is quantum mechanics. This is how quantum mechanics works out everything. The question is it true that we can see some phenomena like that? It is true. In reality, if you look at the next slide, it actually tells us something like that. If you look at this is what we see. You see the peak being skewed. You see the peak being skewed. This is when J over R is significant. When J over R is significant, we've got something like with this a doublet here. This is another doublet here. This is not a doublet, it's two doublets. Now, what about if the distance becomes larger? If the distance becomes larger between them, this is what happened. You see the two doublets here, because they are slightly away of each other. Therefore, you can see them not being skewed that much, And another set here is this doublet, and the other doublet is one here, and one doublet is here, is overlapped with something like that. So the other one. What's the time now? What's the time now? Hans? Okay. I just want to control the time a bit. Oh, we still got enough time to talk about. Okay. In the following few slides, it's about different spectrum. I'm going to go through this because I'm going to go through this very quickly because this is very easy to understand. We'll talk about depth. Depth is slightly hard to understand what everything is additive. But if you look at this figure here, you got S1, S2, S2. You got S1, which is okay. That can collect signal for different groups of CHs. This is CH, this is C2, CH2, this is CH3. So CH works like that. Okay. CH2 works like that. Now CH3 looks like that. Yeah. Now what about this X? This is when the last pulse is 45 degrees, you collect signal like that. Collect 3 signals. When the last pulse is 90 degrees, you collect signal, 3 signals like that. When the last pulse is 135 degrees, you got to collect these 3 signals like that. If you look at when it's 90 degrees, S2, for example, when it's 90 degrees, when the last pulse is 90 degrees, you see that these 2 becomes 0, and you only got CH. And what about this one here when it's 135 degrees? 135 degrees, which is this one here, 135 degrees. You collect this signal. So CH2 will be negative. So CH2 and CH3 being positive but slightly different. Therefore, people do addition of these 3 signals, by using some formula. In the end, we got a depth, like this. Okay. So this is 135 when it's 135 degrees. So you've got CH2 being negative, CH3 being positive, always around this area here, or maximum somewhere around this area. This could sometimes in the extreme case, sometimes you see CH3 as well. But CHs are always in this area here. CH2 could be in this area. And again, because it's a depth 135 is negative. So you can easily identify what CH2 are, where CH2 are, and CH3 and CH. This is very simple. I think you already know that. And APT is better. It gives you quaternion carbons as well. Not simply give you the CO2, it also gives you a quaternion carbon. Okay, and NOE, and then NOE is two-stage correlation. We explain to students that how NMR data are collected, but we're not talking about this here. We're talking about Koji, which you are familiar with, 2 to 3 times correlation, usually homonuclear correlation. We talk about proxy homonuclear correlation as well. Koji is 2 to 3 bond. Proxy is multi-bond correlation. You can see the proxy from here, from this head, the correlation of this head with this head, which is about 6 to 7 bonds away. This is what proxy can do. But Koji can only see this, which is just 3 bonds away. If there is a double bond, proxy can sometimes and often see the 4 bonds away. But Koji can see some 4 bonds away. But proxy you can see plenty of bonds away, depending on the missing time. If it's a long missing time, you can see very long, very far away. So this is proxy. And then you see no-G and rho-G, which is through-space correlation, And HSQC, you know that it's 1 bond correlation. In other words, you see the correlation between this H and this C, this H and this C. And HMBC is multi-bond correlation. You can see this correlation between this C and this H, which is 3 bonds away, 1, 2, 3. And you can even see the 4 bonds away, 1, 2, 3, 4 bonds away. This is multi-bonds correlation. Okay, having finished this, we can step up to biomolecular NMR. We usually deliver the biomolecular NMR, the peptide. As a model molecule, we use dipeptide. And here we got the leucine on the left and tryptophan on the right. And leucine, because it's the first position, that's why we call it simplified by L1 and abbreviated by W2 for tryptophan. And the naming convention is, this is the HD, the delta 1 of leucine 1. This, for example, is a H7 of W2, tryptophan 2. So this is how we label each of the codons. Everywhere is the same thing. This alpha, this beta, this gamma, this alpha, this beta. You can call this gamma, delta, something like that. But people also call 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 2 different conventions. I'll talk about the convention. So this is a model we use for biomolecular NMR. The biomolecular NMR often deal with water, but this is still very small water signal. In protein or peptide, you often need to deal with very big water peak here because you have to observe the NH signal. I'll show you an example, one example with very big water signal. Anyhow, water signal can be depressed. If you do a depression, you see that the depression is somewhere here. It is clear. For 2 peptides, this is not very complicated, which is not too bad. It's not too bad. If you have 10 peptides, 20 peptides, 100 peptides, for 2 amino acid dipeptide, for plenty of amino acids, then the story is completely different. You see this being a bunch of peaks. We'll show you an example. Now, unfortunately, for peptide and protein, we often need to put it, to dissolve it in 99%, 90% D2O. So this is actually 90% D2O, 90% water. This 90%, 99% D2O. So we usually need to dissolve in 90% water and 10% D2O. But if you use 99% D2O, this will get exchanged. This will get exchanged. This will get exchanged. We don't need to observe NH. So we need to understand why they got why we can't observe NHs. Sometimes on NHs are usually often NHs are usually broad. This is also broad, but this is a different mechanism why this is broad. The reason why these two are broad was because they have some exchange with some solvent. Even a little bit of water in solvent to make it broad. This one here will usually broad and not observable because it's in the end, in the terminal of the molecule. It's very flexible, so flexible that it can't be observed. So this is about the observation of angle. We usually count the number of protons and number of carbon, and we usually use HHQC and HMDC, HHQC and HMDC and toxin. For peptide NMR or protein NMR, we are lucky that we have a statistic of each of the amino acids. For example, leucine, we got a statistic like that. For tryptophan, we got a statistic of chemical sigma. Here we can see two conventional naming system. We call this beta, gamma, delta 1, delta 2. And so this is the delta 3. We call this epsilon 1, epsilon 2, zeta 2, zeta 3, eta 2. And also we call it T4, T2, 1, 8, 9, 4, 5, 6, 7. The two naming systems. Both of them are what we use. It depends on what you like. Now, if you keep in mind on this, you can see within this four picture, 1, 2, 3, 4 protons here. H4 appear to have the largest chemical sigma among these four. And CH2 are the beta producers or H beta. Often split into two because gamma and alpha are often and the center of stereocenter. That's why they are diastereotopic. Most of the time, they are diastereotopic. For example, this gamma here, this gamma here, this one. You can see that this is connected to this connected to this connected to H and that. So the delta. So the beta here have a stereocenter here that connected to four different things. Therefore, the beta, the H beta divided, separate into two peaks. So often, but not always. Okay, this is the statistic. We can actually have a look at the statistic table now. I can't have it. Okay, I mean, yes, table, oxy. Can you see the screen there?
Not
This
yet.
screen explains the toxic table of 20 amino acids.
Yes,
20 amino acids.
it's clear.
This is a toxic system. This is another toxic system. We have two toxic systems here and one toxic system here. Toxic system got a system breaker. Whenever there is a pig that has no proton attached, then the system got broken. See that? This is a toxic system. Means that this H can see these H's, and this H, this C, this H, and can see this H, and this H, and this H. But it can't see these two H's because there's a quaternary carbon here that breaks the toxic system. So this table actually gives you the toxic system of 20 amino acids. So that's one of the things we want to really know when we do the biomolecular NMR. We can also show you that there's a statistic. It's a statistic of the chemical shift. So this is statistics of all of the 20 amino acids chemical shift. See that for alanine, for example, you got alpha being approximately that value, and C alpha, approximately that value. If we look at something further, arginine, for example, you got something like it. You got an alpha, you got a beta, gamma, delta. All of them are tabled into a statistical table. That is very handy for us, especially in protein or peptide assignment. Let's get back to this is about okay. So we see that this is the Koji. Koji gives us 2 to 3 bond correlation. Koji of this molecule. And we can see that when we do this in our assignment, we try to find something that we can recognize first. Because this is very easy to recognize the 6 proton here, possibly something here. And from this 6 proton, we should be able to see the correlation between this H and this H. In other words, delta, the correlation between delta and G gamma. See the correlation between delta and gamma. This is gamma. This is gamma. And we should be able to see from gamma. We should be able to see gamma to beta. Gamma to beta. So gamma to beta is something like that. So this is gamma. This is beta. Okay, you're too close. It is somewhere here. And the gamma and beta. After the beta, you should be able to see alpha. Is it true? The beta is something. You draw a line here. You get a correlation between alpha and beta. So using this correlation, we can quickly assign delta, gamma, beta, alpha. And this part here, how do we assign? How do we assign this? We can use the same principle and do the same principle. So take it where this is the expansion of that. Now remember we said that H4 gets the highest chemical value. And from H4, we should be able to assign H5. So H4, CH5. So we know that we draw a line here, we know that this is H5. And what about from H5? Can we see H6? Yes, we can see H6. This is H6. We draw a line here to here, we see that this is H5. Draw a line here to here, see this H6. Right. So we got H6 here. We draw a line to the center, we also see the H6. Right. So from H6, we can observe H7, which is true. We will find the line from the H6. Hc correlated somewhere here we got H7. The correlation between H7 and H6. And then we got H7. Got H7. And there's one thing that was still not assigned. H2 here, which appear to be here because it has an integration of 2 protons. Therefore, it's definitely H2 here. So we got something like that. Using just simply code assign all of the H's in this expansion. And we already assigned the other ones in the other spectrum. So once we assign oxy, then we can have a look at the analogy to see what the indication is. Of course, there's no problem that alpha will see beta, beta will see gamma, gamma will see beta. There's no problem because they're too close, they're very close together. The funny thing, you also see something like H alpha, which is this one here, correlate to H delta, delta correlate to alpha. See how many bonds away? How many bonds away? They are too far away to be seen in coding spectrum. But in node you can see them. Even funnier, we see something like that. It's a very small dot in Broadway. This indicates that. This H4 here, which H4 here, is correlated to somewhere here. The draw line here is here. You see that? This indicates that. This indicates that H4 is correlated to HA. H4 is correlated to HA. So no G actually gives you the true space correlation. It doesn't have anything to do with bond. You see that from HA to H4 is how many bonds? 1, 2, 3, 4, 5, 6 bonds per bond. 6 bonds. So is it true? Let's have a look at it. There's a model, 3-dimensional model. You have no problem. You'll see the alpha beta. No problem, you can see alpha, beta, and so we can also see H2, H2, H4 and HA, H4 and HA. So you'll also see H2 and HB, H2 and HB. H2 is somewhere here. H2 and HB, right? So there's no problem. So all of this indicate that what we see on the NMR spectrum is right, including HA and HG. So the correlation between HG and HA is verified in the 3-dimensional structure. So then we use HHQC. It's time for us to use HHQC. We already assign everything. Every proton NMR, every proton. And then, of course, we can assign every protonated carbon. What about the quaternated carbon? We then have to use HMBC. There's something that you need to remember about HMBC. There are 3 factors that we have to know. HMBC is observed. It's optimized to observe multiple correlation with coupling constant around 8 Hertz. In other words, if the coupling constant between this and this is around 8 Hertz, it appears to be very strong. If it's not, such as this and this, they appear to be weak or not observed. So this is the first criterion. Now the factor is one bond correlation can often be observed as a doublet. If we observe it's a doublet, we have doublet, we have a doublet here. So this correlated nothing. And this correlated nothing. I mean, you see that you draw a line here, there's no peak here. In fact, it's a center of these two components that correlate to something. And this doublet, the center of this doublet, actually indicates that this is a carbon. There's a carbon. This is a carbon that directly attached to with this proton here. Indeed, we say that this is HC2 attached to H2. You read assign this to be H2, remember? This is C2 attached to 2. So this is double. So it appears to be a double. 1 bond and 2 bond. Fact number 3, 2 bond HMBC correlated aromatic rings are not usually observed. For example, this C4 to C4, C, I talk about C, not H. C4 usually don't correlate to C9 and C5 because they are 2 bonds away from C5. C5 to H4, 2 bonds. C9 to H4, 2 bonds. Or H4 to C9, 2 bonds. H4 to C5, 2 bonds. Which is what is pointed out here. This is between CH and H7. C8 to H7. It's not observed. Oh, C8, H7, this is H7, this is H4. So this is very important. In fact, it's generally true if you have 2 bond, 1 bond, 2 bond, 1 bond chain like this in the aromatic ring, which is what we call a conjugation chain. So you have 2 bond, 1 bond, 2 bond, 1 bond, 2 bond, 1 bond. If you had a case like that, you often see phenolical. You don't see this. But there's an exception. If, for example, you've got an OH here or OH here or OCH3 here, or any O something, then you can observe weak correlation. So it's due to the coupling constant, nothing secret. If the coupling constant is close to 8 Hertz or 20 Hertz, you can see. If the coupling constant is too big, you can't see it. It's 38, 40 Hertz. You can't see it at all. Because some of the coupling constant between H and C can be 100 Hertz away. 140, 150 Hertz, even 250 Hertz. So this is a major thing. When you do have low. Okay, this is biomolecular NMR. Let me see if I have some more things to tell you. Okay, I think this is enough talk. To escape from here, we're going to talk about problem solving. Any question about the content that I've talked before? I'm happy to answer any question.
Okay. Thank you, Dr. Wilford. And now we proceed to the question and answer session. Silakan Bapak Ibu atau mahasiswa yang akan menyampaikan pertanyaan bisa disampaikan secara langsung ataupun melalui chat box di Zoom meeting. Dipersilahkan.
Yeah, for the student, you can even raise your question about something that you do a project about, even the NMR assignment where you can possibly try to solve it in this lecture. Because the next step would be problem solving.
Yeah. Okay. Is there any question for Dr. Wilford from the audience? Maybe I will stop the share screen. Yeah. Silakan Bapak Ibu. Okay. Maybe I will start the question, Dr. Wilford. It is interesting about HMBC enhancement because sometimes we have 4 bonds correlation in HMBC. We can see 4 bonds correlation, but it's rare. It's rare, and we saw the intensity is very low. So we should zoom in to make a zoom in NMR processing software so we can see the 4 bond correlation. Is there any suggestion for you how the enhancement in HMBC measurement so we can get clearer 4 bonds correlation in an HMBC experiment? Maybe that's from my question. Thank you.
HMB first is a multi-bond correlation. It's supposed to see from 1 bond to 2 bond, 3 bond. Sorry, from 1 bond. 1 bond is a doublet. And 2 bond, 3 bond, 4 bond, 5 bond. But sometimes, often, you can only see 3 bonds. But when is the time you can see 4 bond, 5 bond? It's when you have double bond or triple bond. If you have triple bond, you can even see 5 bonds away. So it depends on the bonding, So this is the first principle, bonding. Bonding gives you a correlation. The next principle is coupling constant. The coupling constant. If the coupling constant between that proton or the carbon that you want to see is around 8 Hz, then you should be able to see it. If the coupling constant becomes larger than so large that it doesn't even appear on the HMBC, even if they are 3 bonds away, with some attachment, for example, that affect the coupling constant that much, then you won't be able to observe. Did that answer your question?
Yes. Okay, I can get the
same case happened. The
Yes.
same case happened for HHQC. HHQC is supposed to be able to observe 1 bond and 4 bond and 1 bond correlation between H and C. But remember, the condition is it is optimized for the coupling constant being around 140 Hz. If it's around 140 Hz, even if it's 150, 160, 170, or 110, it can still observe the HHQC correlation. But if you are, or somehow, if you get an HHQC, a molecule that has a 1 bond coupling constant, for example, alkyne, terminal alkyne, about 250 Hz, for example, the coupling constant between the terminal alkyne and the C, then very possible that you won't be able to accept the HHQC, observe the HHQC correlation between that 1 bond proton and C. You can observe it if you change the condition of the experiment. There is an experimental parameters that can change so that you can observe something like 200, optimized for 200 Hz or 250 Hz. Then the HHQC peak will be observed, even if it's 250 Hz. Does that answer your question?
Yes.
Does that answer your
Yes, I
question?
get. Yeah. Okay.
Okay.
Maybe we can proceed to the next question, please. Anyone?
Okay, let's step into the next phase. All right, problem solving.
Okay.
At the meantime, when I'm talking, you prepare to ask questions. Everyone can prepare to ask a question. Then we can talk about that, right? I'll try to control it so that at least we have a 5 to 10 minutes to talk about something else. Okay.
You need to share your presentation.
Pardon?
Yeah. Do you need to share your screen on?
Yes.
Yeah.
I'm going to share my screen again.
Okay.
Share my screen again. Okay. Can anyone see the screen?
Yes.
Okay, I'm going to talk about problem solving. Now, for NMR problem solving, the information we need, given that it is a sampling, it's a spectrum, there is a spectrum. Okay. So we need information, we need this information, IR, mass spectrometry, NMR, and chemical shift table. These are the things that we need. If you don't have IR, sometimes it's fine. sometimes it's very helpful. But sometimes, perhaps if you have a good set of NMR spectra, you don't need IR. Mass spectrometry. You got a mass spectrometer mainly to work up the mass, Of course, if you can work up the functional group from your mass spec, it's good. And the other thing mass spec is good is that if you have CL, protein, for example, you can immediately identify from mass spec because one of the mass spec peak will be about 1/3 of the other one. Always 1/3 of the other one. You follow this pattern in the number of places in the mass spec. So you know that there's chlorine. The other thing is bromine. You got bromine because the natural abundance of bromine is about 50% bromine 79, 50% bromine 81. Therefore, in the mass spec, you see two peaks of bromine being about the same height. So this is good about mass spec. Other thing about mass spec, well, we don't actually care much when we do that, when we have a complete NMR spectrum, because NMR tells you much more than anything else can tell you. But mass spec is complementary. If you don't know the molecule, you've got to have the mass. If you don't have the mass, there's no way they can have a good guess, unless you know possibly from your previous precursor of the reaction, then you may be able to figure out without doing mass spec. But the good thing is that mass spec gives us molecular weight. Okay, software. What are used? Excel, ChemDraw, Narasumber. These are the software tools. Of course, there are some of the good tools as well, which you can use, and you can browse the internet to get, such as ChemDraw, such as what you call Molto. I'll show you later on. Right. So the general procedure is something like that. You start with finding the functional group. For example, what's the CW bond of a new group? How many CHs? How many CH3? How many CH2? Etc. Whether or not there is an aromatic ring, how many alkenes, etc. Now, molecular weight we have to use. Mass spec. Oh, something good about mass spec is actually it will indicate whether or not you've got nitrogen or fluorine. Nitrogen, if you get an odd number of mass, molecular weight, of course you've got nitrogen. It's either one nitrogen or three nitrogen. One or two, often one. Okay. So mass spec is good. Got to go out with molecular weight. Now, primary molecular structure, we need to figure out how many C's, how many H's, and how many something else, O's, N, etc. You need to, once you work out the molecular structure, primary structure, how many C5, H9, CO, N, O3, for example, then you use IHD to work out number of multi-bonds, number of triple bonds, rings, etc. So the hydrogen efficiency index of hydrogen efficiency. Okay. And then you start to wonder whether or not they are equivalent nuclei. For example, if you have a di-substituted, a para-substituted aromatic ring, para-substituted aromatic ring, then if it is para, obviously you have two equivalent carbons and 2 equivalent protons, right? Because they are parallel. And also, you need to think about the symmetry. Sometimes you're given a small, a very simple NMR spectrum, but the molecular weight is big, in which case you can think of symmetry. Now, this is important and interesting. Once you work out the structure, you confirm that you get a structure, good or not good, bad, correct or incorrect. You try to fit the molecule into something, some website like ChemSpider or more molecular form. I'll show you later on how to get into and search. Then once you are happy from where you can often find a structure that meets all of the conditions that you have. Well, by condition, I say that how many CH3, how many aromatic ring, what kind of substitution of the aromatic ring, whatever di substitute aromatic ring or mono substitute aromatic ring, etc., etc. You can quickly figure out what structure it could be. Now, you get more than one structure that is possible that meet your requirement. And then what you need to do is enter into ChemDraw to predict the center spectra to see which one would look more like your spectrum. Some of them can be quickly ignored because they are so different from the predicted NMR spectrum. So, and then in the end, you analyze it using Narasumber. At the moment, this is the best NMR processing and analysis software in the world. So this is a general procedure. Let me give you an example. Okay, I'm going to show you some example with this. All right. I'm going to see you first. Okay, this is a molecule that we have run recently, and it's kind of relatively simple. Yes, it's simple. See that it's very simple. It's very simple. But then it's telling us that the molecular weight is 284. Let me see. 294. So it tells us that the molecular weight is 294. Let's write it down. Molecular weight is 294. Okay, so molecular weight is 294. See, this is a big molecule. Mass spec tells us the molecular weight is 294, but it only got a few NMR signal. Now, if you look at it closer, let's look at it closer. We've got an E for expansion, escape. For escape. Then if you do integration, for example, I for integration, this one here, and this is supposed to be, this is quite probable. Oh, this is solvent. We can't separate this. Okay, now how many peaks do we have? How many peaks do we have? Peaks. So we got 1 here, integration, 2 here, integration, 3 here, 6. You got a 6 peak, 6 protons. So what we got is we got 6 protons. Let's call out. Okay. Maybe I need to look at somewhere here. Right? We got 6 protons. We got 6 protons here. Now we have another do integration here as well. Let's do the integration here as well. This is supposed to be 1 proton, and this is supposed to be 3 protons. So we got how many protons do we have? 6 protons in this area, here, 6 protons, and 3 protons in this area. So we got 9 protons. So we got 9 protons. Okay. 9 protons. That's okay. 9 protons. I got 9 protons. All right. Just avoid confusion. So we got 9 protons. Now, how many carbons? We look at carbon here. You see that this is 6. There must be 6 protons, 6 carbons here, because this is alkene area. 7 point something to 6 point something. 6 to 8 is alkene area. So you got integration of 6. You must have 6. You must have 6 protons. You have 6 protons because they are all alkene protons. You must have 6 carbons. Right? 6 carbons because they are all alkene protons. So there are 6 carbons here. There must be 6 carbons here. So we do the PPK. 1, 2, 3, 4. Although we see only 4 protons, 4 carbons, but we should say that there are 8 protons here because they have 6 protons here, 6 CH here, not 6 CH here. You got 3 carbons here. This is quaternary carbon, right? And you got 1 CH3 here, and CH3 is somewhere here, right? Which is OCH3, must be an OCH3. Therefore, with the component we have OCH3, the 6 carbon. How many carbons? 1, 6, 7, 8, 9, 10. Okay? So we got 10 carbons. So we change it to 10 carbons. So we got 10 carbons. Now, from this one here, we have a C11O. Agree? This location must be C11O, nothing else. So this is C11O. We got the OCH3 here. Agree? Because the CH3 in this location must be OCH3. There's no other way. The CH3 in this location must be OCH3. Therefore, we got 2 O's here. One is somewhere here. One is somewhere here. Right? So we got 2 O's. We got 2 O's. Now we work out the chemical. Look at molecular weight of this one. It's 161. So this is 12 is 120, 1 is 2, 2 is 22. 2 is 24. 2 is 32. Right? 32. So we add this up, it's 161. But we have 294, it's far bigger. Then it's a time for us to think about the chemical equivalent of symmetry. In this case, it's far too small for what we have. So we think of symmetry. Now what we think of 2 structures like this, or 1 or 2 aromatic ring, for example. 2 aromatic ring, for example. Right? Then you add 6 more. 24, 2 aromatic ring, we add 6 more. 6 more. And then it is 6 more. But we also have because it has to be symmetry. So here, and this is, and alkene and alkene NMR, alkene proton. So if you look at this, there's an alkene outside the aromatic ring coupled to somewhere here. And this is actually propane. See, this alkene here. It's coupled to somewhere here, coupled to something here. We didn't need. Right? So this alkene coupled to somewhere here, something here. See that? There's a coupling here. So there's alkene outside the aromatic ring. So you say that there are 6 protons here. 4 protons inside the aromatic ring. 2 alkene is outside the aromatic ring. How does it happen? So there must be also something more here, right? Something more here, rather than one ring, two rings. So we have the multiple ring. This 6, including 2 alkene, could be this one. It's obvious that this is the pair substituted. We've got two alkene. Then this we count this as 6 before, 6 carbon before. Now, because of symmetry, there must be 12 carbon. So we change it to 12 carbon to see what happens. So it was. What about we start simply make it 20 carbon because symmetry? Okay. Make it 20, see what happens. Well, because of this, because of symmetry, we also have this double, right? This double, and have this double. Right? By doing this, we found that it's something like that. So we got 28 left. The molecular weight is, no, 28 too much, 28 too many. 28 is usually a proton plus an oxygen, an oxygen. So we got too many protons here. Sorry, too many carbon here. That's too much. 28 too much. So we got 1 less carbon here, make it 19. So we got 1 less O here, make it to 3. Now we substitute this into this, and we found that we got the primary structure, which is this one, right? So we got C19, H18, O3. Very simple. That we make up this one. Having said so, we are not sure that whether or not this is true. But just remember that we got 2 elements. We got something that is symmetry. Okay, let me substitute and copy this. Control C, copy this, and go to the net to find it. Go to the net to find it. Let's go to internet. I'm going to find the internet here. Right? No, not from here. From here. The chem spider. That's the chem spider. Control, click. Chem spider. So this is chem spider, right? With which you can actually enter the structure, Control V to enter the structure, and do a search. It will take a little while, but then you get everything. Got every possible structure that we give you. Remember, we got 2 aromatic rings and 2 di-substituted, para-substituted aromatic rings. So anything that is not related to Earth, let's forget it. We also got about CH2 as well, and nothing. Got an OCH3. So this is nothing related. It's scroll it down. So this is di-substituted. But OCH3, boys, we got it. Incredible. We got something like that. Okay. So this is a quick way to find it. Another way to find it, another place to find it somewhere here. Okay, let's try this control click. It's called more. Again, you enter the structure here, the primary structure. Let's see how we can find it. This is not related. It's not related. Oh, this is close, but it's not para-substituted, right? The OCH3 is not para-substituted. It's auto-substituted. So we find something, or you can try auto-substitute it but that doesn't meet our NMR structure. Okay, fine. In fact, from here you can already guess. Then you can use this structure. Okay. Now enter this. Sorry. You can enter this structure into can draw and predict it, and enter the other previous structure. And you can see that into can draw and compare the spectra that draw. 20 of them, there are possibly 100 of them, or possibly more, 200. Sometimes I got about 200. But the one that meet our condition are not many. So using this, you can quickly get a structure. Then you can go to ChemDraw, and do the structure prediction. I have done this. Okay. So the next step is to go to ChemDraw. So you go to this one here, right there. Go to OCH3 here. Go to something like that. Remember, there's alkene. Sorry. This is the structure that we have. Over here, alkene here. Okay. So OCH3 here. It's OCH3. There's an O here. Okay, we do a prediction to see what happens. You see? That's what we got in our spectrum. That's how to get it. You can enter different structure. For example, the structure that have with the OH, the OCH3 being somewhere here, you see very different spectrum. You can even do the carbon and spectrum. All point to the direction, point to one point in the air. This is the structure. So this is how we solve the problem. But sometimes they are very different. So this is how. And then we do the assignment to save the time. I see a lot solution so that we can have a look at it. We'll see. Wow, we don't have time. Okay, this is solution. Well, we can do the assignment easily. This is Koji assign the 2LP. We work out that in this area here, expand this area. You see that this alkene is coupled to this alkene. It's the first component and the third component here that is coupled to this. And on the other hand, this doublet is 2 protons here, coupled to another doublet here, which is the second component and the fourth component. So the second component and the fourth component to this doublet. Each of them represent, each of this one here is 4 protons here. 1, 2, 3, 4. 1, 2, 3, 4. Yeah. So this is how we solve the problem. Sometimes they are difficult. Sometimes they are difficult. For example, this is a bit difficult. The difficulty comes from the fact that we can't actually get a structure from the internet. So we were given the molecular weight is 289. Well, 289, we can guess that. That's an N. That's an N. And then we count the number of carbon, we count the number of protons, There are how many protons here? 1, 2, 3, 4, 5, 6, 7, 8 protons, plus this one here, plus this one here. This is 6 protons, 14 protons here. So to start with, we have we have 15 protons because one of them is NH, one of them is NH. Or if we get more than that, this is 1, 2, 3, 4, 5, 6, 7, 7 here, 7, 8, 9, plus that. So we got to 9 plus 6 here. So 6 here. So 15 protons here. We got 12 carbons here. The 12 carbons here. The 7 here, at least 7, 8, 9, 10. 1, 2, 3, 4, 5, 15 carbons. The reason I say 6, 8, 7 here because the proton showing that that's 7 protons. Right? So the 7 protons, 7 alkene, 7 carbon. So this is how we work out. So in the end, we know that there are carbons here. There are 15 carbons here. There are 15 protons. The one end here, these are all we confirm. We also confirm that there is an OCH3, an C double one O here. So we enter one O here, see what happens. Then you got 64 left. Compared with this, you got 54 left. Right? What is 64? You can have 4 O's, you get 2 O's, 1 S, or 2 S. Right? So this is a very good figure. 64 is a very good figure. In the end, we say, well, why don't we try this? Because it's rare to have 2 S's. So we have 2 O's, add 2 more O's here, add 2 more O's here, and 1 more S. And we got some structure like that. When you enter the chem slider, enter the chem morpho, you can't find any structure like that. You got something similar, with this being somewhere here, even this being somewhere here, here. But we prefer this being somewhere here and this being somewhere here, because we know that from proton, it is triple substitution. There's one ring that's triple substitution. But again, this one can be here and can be here as well. So we enter this structure, possible structure, into ChemDraw and find that in the end, this one meets the condition. All right. I still have something to show you, but it's too little time to talk about. I think we might as well stop.
Okay.
Okay. quickly show you in
Yeah.
1 minute. 1 minute. Okay?
Yeah.
Complexity. Complexity of protein NMR and peptide NMR. This is about 100 and something megabytes here for the solution. It is a 9 amino acid peptide, and we are using it to create something useful in medicine. We've got 2 minutes. I'm going to show you 1 minute. Okay, I said the water will be very big, so big. See the water? So big. And we can suppress the water. Boom. You see how complicated the structure is? A lot of overlapping. There's alpha area, there's beta area, gamma and delta area. This is beta area. And this amino acid area, NH area. So we do the sort of thing. We assign everything here by looking at the toxic side. This is not here, but the toxic looks like that. Okay. You see, focus on this section here. You see that this is toxic pattern. This toxic pattern. A very clear toxic pattern. And because of toxic pattern, we allow us to assign the amino acid, the 9 amino acids assigned here, and there. And then we go to Cody, and then we go to Cody. See, Cody is just so simple. There's no toxic system here, 2 to 3 bonds. This is NH, backbone NH and C alpha area. In the end, you assign everything. You assign everything. And we also have the heteronuclear spectra as well. Okay. I have question. I have time for you to ask questions.
Yeah. There is another question from the audience, please. We have
yes, I'm going to stop my sharing so that
session.
Okay. Oh, you stop my sharing. Very good. Very good.
Yes, please. Oke, jadi Bapak Ibu tadi dan mahasiswa juga tadi Dr. Wilford shown us the way how we can solve the NMR spectra so we can get the information about the molecular structure from our research ya. Jadi struktur molekuler tadi sudah bisa ditentukan dengan data NMR. Jadi untuk mahasiswa struktur-struktur yang ada di buku kimia itu salah satunya adalah ditentukan melalui NMR ini, gitu ya. Khususnya untuk molekul-molekul organik. Gitu. Jadi memang molekul-molekul tersebut bukan buat-buatan imajinasi ya, tapi memang ada gitu. Ya, please from the student one question. Okay. Yeah, Dr. Wilford, maybe the students still try to get in. Oh, yeah, Bu Vera. Please, Bu Vera.
Thank you.
Head of department. Yeah.
Okay, Dr. Wilford, in
no worries.
Determining the structure of amino acid, you use 3-solvent system to get a good spectrum. Do we have to use the same way to determine the structure, maybe the structure of a chemical compound which has many sugar units?
Could you repeat the question, the body of the question again? I can hardly hear you.
Okay. In determining the structure of amino acid, you use a 3-solvent system to get a good spectrum. Do we have to use the same way to determine the structure? Maybe a chemical compound which has many sugar units in it.
The first step is to get a good NMR spectrum, a set of good NMR spectrum. If you have proton, carbon, better to have APT, like carbon, tell you CH2 and CH3, and Koji. If you work with peptide, you need toxin. If you are not working with peptide, you don't need toxin. Because Koji, because small molecules, through bond relation is very simple, right? So if you want to work out the folding of the molecule, folding or the secondary structure of the molecule, you need node. And then what you need to do is to have HSQC and HMBC. One, for small molecule, you got Koji, HMBC, HSQC, proton, carbon, 5 spectra that we do. Now, to try first, you look at the proton carefully. Proton has sometimes given a lot of information, although sometimes it's very simple. It was a lot of information. For example, if there is any alkene's proton, it will appear between 6 and 9 ppm. Because alkene proton could be either alkene CH or alkene CH2, right? But usually, alkene CH2 is in the other part of the NMR spectrum. So we can actually identify them easily. But if they are in between 6 and 9 ppm, it must be alkene CH, alkene CH. So if the integration is 6 or 9, we know that there are 9 protons, 9 carbons. So this is where to start. And functional group is also very important. If you look at chemical shift table, it tells you a lot of things. Hans, can I share screen, Hans? I'm going to share my screen again.
Yes, you can share your screen.
Okay, I'm going to share the screen. Did I share my screen? I did, didn't I?
Yes. It's a reminder.
So I need to maximize it. How do I maximize? I lost my screen. Wow. Did I lose my screen?
Not yet. Maybe you can
lose
stop
screen.
first and restart the share screen.
I can't see my screen now. I can't see my screen now.
Yeah.
Maybe you can stop the screen.
My screen was minimized somewhere. Oh, okay. Maybe I stopped sharing first. I may be sharing different things. Okay, here. Okay, I'm going to start sharing again. It's better to share the whole screen. You are screen sharing. Stop sharing. Somehow, I can't see my screen. I can't share my screen. What do you see on the screen?
The Excel of
Okay, where's my video screen?
of
Meeting control. Wow, 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 wow. I lost my screen. Am I maximize it?
That's okay. You can explain without the screen, I think.
I seem to have lost my screen.
You can close the screen first.
Somehow I lost my screen if I share my screen. No. Sorry. Now I can see you, but okay. Chemical sheet.
Yeah, maybe you just explain without. Yeah.
You can look at the. Okay. You can bring up. I'm going to put my chemical. Going to open the chat. Even chat. Okay. Control V. Can you see on the chat panel that I give you a website web address?
Yes, I'm
Getting to
opening
that
the link.
web address. I'll tell you something.
Yeah, I'm opening the link, and
Oh, good.
it's
Put it on the screen. I don't know why I lost the screen. Yeah, scroll it down, down. Aha!
okay.
And that's the chemical sheet table.
I'm at the bottom
Control
of the page.
Control
Yeah.
plus.
Yeah.
Control plus. Okay. If everyone is happy with this table here, this table is very quick,
zoom in.
useful. Yes, scroll so everyone to see the table.
Maybe Pak Han a little bit trouble.
Yeah. Okay. If you can't, usually I use Control plus to do it. Okay. If you look at this chemical shift table at the center, you see where the OH, where the CH3s are very good. You see where the CH3 are? It's somewhere in between 2 and 4, isn't it? Between 2 and 4. You will also see, you see one, okay, make it this way. 3 and 4 contain all CH3 or CH3 that attach to something that has high electronegativity, element with high electronegativity, NO and C double bond O, and also Cl, phenol, and phenol as well. You see that? So when CH3 is connected to something like that with high electronegativity, the chemical shift is increased. In other words, shift to the left. Otherwise, the chemical shift usually on the right side of the spectrum. So this is useful. Alkene, for example, from 5 to 7. You see the alkene? There is an alkene inside the ring and outside the ring, but it is a bit vague. And sometimes it's not correct. Anyhow, if you consider this an alkene area from 6 to 9, it won't be wrong. And interestingly, you got C double bond OH, and around 10 to 10. So if you see any patches around this area here, 9 to 10, that might be a double bond O. About the OHs, they must be broad. It's spread everywhere, usually are broad. You can hardly see any OH that is very sharp, because OH exchange with anything that it could be very easy. If you look at it on the left corner, left bottom, these sealing groups and sealing groups. Okay. If you look at the first, when the desealing group is O and halogens, which is group 7 molecule. Can you see this? Left corner, left bottom. No, on the screen. Left corner on the screen. So you see that O and halogen, and phenol is also like that. You see the phenol, in terms of the electronegativity, will be less intense than this string, but it is also electronegativity very high element. There's a pi bond, double bond. See, aromatic ring are actually double bond because this double bond can change around. So this is also making it shift to the left. Chemical shift value around 69. And this one alkyne, terminal alkyne, is terminal alkyne. Usually the chemical shift on the right side. So this is chemical shift table. Well, I got a very detailed chemical shift table. I have been showing you this morning because of the time. And now it's the problem of the string sharing. Weird. Okay. I can possibly change the screen sharing there. No, I completely lost my screen control. I completely lost my screen control of Zoom.
Yeah.
Sorry. And there's also a carbon table as well. And once you know that, you will work out the functional groups. When you solve this, you can work out the functional group. Once you have the functional group, you can kind of guessing what kind of structure it is. Does that answer your question? Oh, sorry.
Okay, thank you.
Bu Vera?
Ya, Pak Hanan, sudah.
Okay, thank you, Dr. Wilford, for the explanation. I think we are in the end of this guest lecture series for today.
Yeah.
Thank you for Dr. Wilford that delivered the knowledge about NMR from the basic and quantum chemistry to the application of determining structure based on the NMR spectra. So maybe the students still processing the knowledge of your talk, and I and Bu Vera facilitating all the students if they have any questions. So I will send it to your email. Is that okay?
That's not a problem. We can even have another tutorial meeting.
Okay.
Zoom tutorial meeting.
Okay.
Which is more,
Jadi,
which is better because it's more relaxed.
Ya. Oke. Jadi teman-teman mahasiswa kalau ada pertanyaan silahkan disampaikan kepada saya atau Bu Vera atau Bu Yusi atau Bapak Ibu dosen yang lain juga silahkan. Nanti akan disampaikan kepada Dr. Wilford. Okay. Dr. Wilford, once again, on behalf of Chemistry Study Program of University of Jakarta, for sharing your knowledge about NMR, and also Ibu Dekan yang sudah hadir pada kegiatan pagi hari ini, Bapak Ibu dosen dan teman-teman mahasiswa juga. Kemudian di sini juga kebetulan ada beberapa peserta yang berasal dari luar UNJ, juga terima kasih atas kehadirannya. Kita insya Allah akan bertemu lagi for the next guest lecture series on Saturday ya jam 10 pagi. Jadi mohon untuk bisa hadir kembali. Once again, thank you Dr. Wilford, and maybe we will have a photo session. So I invite all the participant to turn on the camera. Silakan menyalakan kamera for the photo session.
Oh, really? Can you
Yeah,
really
okay.
do it?
Okay.
How do we do it?
Yeah. We still can have a photo session even it's online.
Oh, good.
Ya. Oke. Ya, kita mohon dipasang senyumnya. Keep smiling. 1, 2, 3.
Really?
Okay.
That was impressive.
Yeah. Okay. Next screen. 1, 2, 3. Okay. Yeah. Thank you for your
Maybe I should
attention.
take off my. Don't worry.
Yeah, it's okay. Thank you for your attention for all participants, and see you on the next guest lecture series. And Dr. Wilford, you can continue your next agenda today. Maybe you will go home directly from the office. Yeah. Okay. I think I will end the Zoom meeting. Assalamualaikum warahmatullahi wabarakatuh.
Thank you.
Thank you, Dr.
Assalamualaikum.
Wilford. Waalaikumsalam.
Waalaikumsalam. Thank you,
Selamat sore,
sir. Thank
Dr.
you, Pak
Wilford.
Herman.
Yeah.
Thanks, everyone.